All right, today we're going to tackle one of the most elegant and, yeah, sometimes mind-bending concepts in all of programming, recursion. We're going to look at how a function can actually call itself, and more importantly, how the computer keeps track of it all without getting totally lost. So let's dive in.
Okay, I know. It sounds like the setup to a really bad computer science joke, right? But stick with me here. Because the answer to this question is the key to understanding everything. Not just how a function can call itself, but also what happens when that whole process goes spectacularly wrong.
So first things first, let's just get our heads around the main idea. What does it even mean for something to be recursive? We're going to start with a really simple physical analogy that I promise will make it all just click. And at its core, it really is that simple. But the implications, they're huge. See, instead of trying to solve a huge problem all at once, a recursive function just solves one tiny piece, and then it calls a brand new copy of itself to solve the next tiny piece. It is an amazing strategy for breaking down a big, intimidating problem into smaller, identical, and much more manageable chunks. The Russian nesting doll is the absolute perfect mental model for this. So think of the action of opening a doll as our function. Every single time you perform that action, you find a slightly smaller version of the exact same problem inside. You just keep calling that open doll function over and over until you finally hit that last solid little doll that you just can't open anymore. Now, for any of this to work, every recursive function needs two absolutely critical parts. First, you've got the base case. In our analogy, that's the smallest doll. It's the stop sign. Without it, you just keep opening dolls forever. And then you have the recursive case. That's the part that does a little bit of work and then calls the function again, but with a slightly simpler problem, moving you one step closer to hitting that base case. Okay, so a function can call itself. Got it. But how does the computer keep track of all of this? I mean, if a function is halfway through a job and then calls itself, how does it remember where it left off? Well, the answer is this incredible, crucial data structure called the call stack. Think of the call stack as the computer's short-term memory for functions. It's like a to-do list, but with a very specific rule. You can only add new items to the top, and you have to finish whatever's on top before you can touch anything underneath. This whole principle is known as last in, first out, or LIFO. And trust me, it is fundamental to how this whole thing works. The stack of plates analogy is just perfect for this LIFO idea. When a function gets called, you put a plate on the stack. If that function calls another one, boom, you add another plate right on top. And if you want to get to that plate at the very bottom, you have to take off every single plate on top of it first. The last one you put on is always the first one you take off. So what exactly are these plates inside the computer? Well, in computer science, we call it a stack frame, or sometimes an activation record. It's basically a dedicated chunk of memory that holds all the information a single function call needs to do its job. So what's actually on one of these plates? A stack frame holds all the context for that one function call. It's got the inputs, any local variables it creates, but the most crucial piece of information, the absolute VIP, is the return address. You can think of it like a bookmark or a GPS coordinate, telling the computer exactly where it needs to go back to once this current function is done. All right, enough theory. Theory is great, but let's make this real. We are going to trace a classic recursive example, step by step, and actually watch how the call stack builds up and then unwinds to give us the final answer. It's pretty cool. We're going to trace the factorial of 3. Remember that from math class? It's just 3 times 2 times 1. Here's how a recursive function thinks about it. The base case is simple. The factorial of 1 is just 1. For any other number n, the factorial is that number, n, multiplied by the factorial of n minus 1. So let's watch the stack handle this. So first up, we call factorial 3. But wait, it can't solve 3 times factorial 2 yet, because it doesn't know what factorial 2 is. So it pauses, puts a plate on the stack, and calls factorial 2. Then, of course, factorial 2 does the same thing. It pauses to wait for factorial 1. Finally, factorial 1 gets called, and bam, it hits our base case. The stack is now 3 plates high. And now for the satisfying part. The stack starts to unwind. Factorial 1 knows the answer is 1, so it returns that value, and its popped off the stack. Control goes back to factorial 2, which was patiently waiting. It can now finish its job. 2 times the 1 it just got back, it returns 2, and its plate is popped. Finally, we're back where we started. Factorial 3 gets the 2,
calculates 3 times 2, and returns our final answer.
And there we have it. The last plate is popped off the stack, and our program has its answer, 6. The stack is now empty again, just waiting for the next job. So recursion is powerful. It's elegant, but it has a dark side. It comes with a pretty big risk. What happens if our stack of plates just keeps growing and growing and growing with no end in sight? Oh yeah, if you've ever written a line of code, I am willing to bet you have seen this absolute nightmare of an error message. This is the computer screaming at you that its stack of plates grew way too high and the whole thing came crashing down. See, the call stack isn't infinite. It's a specific, limited block of memory. Each one of those recursive calls eats up a little more of that memory. So if the calls just never stop, you eventually run out of space, and the program has no other choice but to crash. Hard. So what's the number one culprit here? It's almost always a bug. You've either forgotten your base case, or you've written it in a way that it can never be reached. It's exactly like having a set of Russian nesting dolls that just goes on forever. You'll never find the end, and you'll just keep adding plates to the stack until there's no room left. But what if there was a way to write a recursive function that completely avoids this problem? Some programming languages support a really clever optimization for a specific style of recursion. It's known as tail recursion. Okay, so a function is tail recursive when the recursive call is the very, very last thing it does. That's the key. There can't be any lingering calculations, no multiplication or addition that needs to happen after the recursive call comes back. The function just calls itself and immediately returns whatever value it gets back from that call. Just look at the difference here. On the left, our normal recursion has to wait for the inner call, for factorial n minus 1, to finish before it can do the multiplication. That waiting is why it needs a stack frame, to remember what it was supposed to do. But look at the right. The tail recursive version does its multiplication first, and then it passes that running total into the next call. The recursive call is the absolute final thing it does. There's no pending work. And this is where the magic happens. The compilers for some languages are smart enough to spot this tail recursive pattern. And when they do, they perform this amazing trick called tail call optimization. Instead of adding a new plate to the stack, the computer realizes, hey, I don't need the old one anymore, and it just reuses the current stack frame for the next call. The stack never grows, not even by 1. It completely prevents a stack overflow. So this brings us to one last really important question. If this optimization turns a risky recursive function into something as safe and efficient as a basic loop, why on earth don't all programming languages do it? Well, the answer gets into some really interesting trade-offs in language design, things like performance versus having a clear call stack for debugging. It's a fascinating debate and a perfect rabbit hole for you to dive into next. Thanks for joining me.